Hi everyone, welcome. Today we're going to be talking about the Apache Arrow project along with Apache Spark and their history together as two incredibly impactful open source projects in the data engineering space. This is in celebration of the 10th anniversary of the Arrow project, which has been around for a good decade and has had a huge impact in terms of the data engineering ecosystem in general.
Nowadays, it almost guaranteed that Arrow is probably somewhere in whatever data stack you're using, even if you're not using it directly. So what matters is understanding why it exists and what it's useful for.
I'll also be talking together with Matt Topol, who's one of the PMZ members of the Apache Arrow project and co-founder of Columnar, along with others that might be interesting to you.
Arrow's strength is in the network effects. It's in the interoperability. Because Arrow is this low-level underlying technology that is utilized by all of these tools and utilities, the sooner the data is in Arrow and the longer you keep it in the Arrow format, the more effective, the more efficient all of this will be in your entire pipeline.
So first, let's get into PySpark specifically and how it relates to the core Spark JVM. PySpark is not a Python implementation of Spark itself, but instead a Python wrapper around a JVM-based core engine that constitutes the core Spark that we know. This means that when you write a data frame operation such as, dataframe.filter or something similar, Python will construct the query plan and then hand it to the JVM itself, which then optimizes, distributes, and executes the query, but Python itself doesn't actually touch the data.
Because of that zero copy, zero serialization aspect of Arrow, you can actually get data directly from the Python runtime into the JVM by just actually sharing the raw memory and not having to serialize, deserialize, not even having to do a copy. You can literally just give pointers to memory buffers to the JVM, and it works because the Arrow format is a format, it's a spec. It is identical in memory bytes, no matter what programming language or system you're operating on. And so you can just share the raw memory buffers.
This design means that data operations are equally fast in PySpark and in Scala. Python code only builds the plan with the JVM then executing it. So this is why there's very little performance difference between running built-in functions regardless if they're in PySpark or in Java or Scala. The problems tend to start specifically when your code actually needs to touch the data. So examples of this are user-defined functions using two pandas, or data frame operations that use pandas, custom data sources, or anything where the data has to cross the JVM and Python boundary. That boundary is known as the serialization wall, which means that you actually have to translate the actual data between JVM and the Python processes.
That kind of communication of large amounts of data is very expensive and tends to actually be a bottleneck in a lot of Spark systems. And that's why a lot of systems and designs for a lot of Spark things involve very much utilizing pure JVM functions or pure Spark functions and how you operate on the data and how you even read the data in.
For most of Spark's history, the only way to do this was through Pickle. So before Arrow was introduced, every single byte of data that had to cross the JVM and Python boundary actually had to go through Pickle, and so you would use Pickle to serialize and deserialize the data. The really big bottleneck here was that you had to do this for every single row that was moving between the JVM executor and the Python worker itself. So for example, if you had a partition of 1 million rows, that would be 1 million serialized operations on the JVM side, and then 1 million deserialized operations on the Python side. That would be 4 million serialized and deserialized operations, plus the 1 million function calls, resulting in 5 million operations per total partition. The serialization costs dominate the function cost in this space. And so if you had a user-defined function, like say, return some value times, 1.1, the arithmetic would actually take nanoseconds to execute, but the Pickle overhead was in microseconds. And this would just substantially over time result in performance bottlenecks for these transport operations.
You had to serialize it over there, deserialize it over there, and you're spending the majority of your CPU time just doing that serialized and deserialized steps. And so the initial motivating factor of Arrow was that kind of interoperability where you could have a format that doesn't require that serialized, deserialized step, but in order to do that, it needs to be very efficient to operate on in memory.
This was the world of PySpark pretty much between 2015 and 2018, and then Apache Arrow came along and completely changed it. Let's talk a little bit about the Apache Arrow project. So Apache Arrow was conceived in late 2015 by 3 people who independently hit the same technical limitations. The first was Wes McKinney. Wes McKinney was the original creator of Pandas and had spent years fighting Pandas as memory models. In 2015, he published a blog post entitled Apache Arrow and the 10 Things I Hate About Pandas, where he documented the specific problems that Pandas had, specifically around having no memory mapping support, poor database and file ingest performance, and opaque memory allocation. His rule of thumb was that users needed around 5 to 10 times as much RAM as the size of the data itself. The second founder of the project was Jacques Nadeau, who at the time was involved with Dremio. He was building a query engine that saw every single data system and saw them have its own internal memory format. In this role, he saw how moving data between systems meant serializing and deserializing at every single boundary, creating a ton of overhead complexity and interoperability problems for any given number of systems. The third was Marcel Kornacker. Marcel was the creator and principal architect of Apache Impala at Cloudera. You saw the same copy problem within the Hadoop ecosystem itself. The data was being converted between formats at every single system boundary, burning CPU and memory on work that produced no analytical value.
There was a lot of discussions amongst the initial creators, Wes McKinney, Jacques Nadeau, and many of the Parquet maintainers were also part of those discussions, and many of them are also some of the original Arrow developers too, because it was just seen that you need this kind of, you have your on-disk optimized formats of Parquet, and you need some efficient way to represent it in memory to operate on. And that's where Arrow came in. And that's kind of the key difference.
According to the online sources that I saw, they met at Strata at NYC in September 2015 and then moved towards building the standard. Arrow then entered the Apache incubator with the Apache Software Foundation in February 2016 and then graduated as a top level in July 2016. There was only a 5-month incubation period, and so this reflected a lot of the broad industry consensus behind the project. The core idea of Arrow was pretty straightforward. Arrow defines a language-agnostic and in-memory columnar data format that is now implemented in over 13 programming languages. The specification dictates how data is laid out in memory, right down to the byte alignment, the null bitmap encoding, and the buffer ordering.
Arrow is kind of analogous to, say, JSON. It's a spec, it's a format. It has implementations in every language under the sun. It has all of the properties that make something like JSON ubiquitous, but is ideal specifically for the use case of data transfer, data interoperability, data engineering.
When two Arrow-aware systems exchange data, no conversion is needed. The bytes in memory are already in the right format. This is what's called zero copy. The same memory buffer that one system wrote can be read directly by another system without any transformation. In traditional row-oriented layouts, which are the most traditional databases, Python objects and Pickle store data, so all fields are row-oriented and stored contiguously. This is great for looking up single rows, but terrible for scanning single columns. If we want to look at a columnar layout by comparison, which is how Arrow stores data, all the values are single columns and stored contiguously that way. It's great for analytical queries that touch a few columns across many different rows. What makes Arrow special, however, is its CPU cache efficiency. Modern CPUs fetch memory in a 64-byte cache line. When the CPU reads one value, the entire 64-byte block containing it is loaded into L1, L2, and L3 cache. For example, in a columnar layout, a single cache line from, let's say, an age column can hold 8 int64 values, which are all useful for selecting the average of age in this case. In a row-oriented layout, the same cache line will hold one row's mixed fields, most of which are irrelevant for the operation that we're trying to perform. The cache hit rate then approaches 100% for columnar single column scans versus as low as 7% for row-oriented scans on wide tables. The second reason why columnar is so interesting is because it leverages single instruction, multiple data methods, also known as SIMD. If we take different architectures like 128, 256, or 512-bit, we can optimize the evaluation of values by densely packing them in a homogeneous typed array, which is what a columnar format provides. For example, a predicate like where salary is greater than 70,000 can be evaluated on 16 values simultaneously on a single AVX512 instruction, 8 values on an AVXX2, which is 256-bit. The last note on this should be vectorized execution, which plays a major role in Spark itself. In 2015, a paper was published that formalized the insights that processing batches of 1,000 to 2,048 column values through each operator instead of one single row at a time resulted in much faster performance. This function call overhead here is amortized. with the CPU pipeline staying full and the data staying in cache. Arrow's batch-oriented design was built with this model in mind, which is oftentimes the distinction we hear in Spark around vectorized batch versus row-by-row execution. It was in Spark 2.3 in February 2016 when Arrow first entered into the Spark ecosystem. This began with a very specific single pain point, aka to optimize the dataframe.toPandas operation that was at the time extremely slow. The Jira ticket which was filed was called Implement Apache Arrow Serialization for Spark Dataframe for use in dataframe.toPandas, and this was filed by Wes McKinney himself in February 2016, and then resolved in 2017, and then shipped in Spark 2.3 in February 2018.
With the start of things like Pandas that leverages Arrow into the hood sometimes, or is able to leverage Arrow into the hood, and even more so now with Polars, which is entirely built on Arrow, all those data frame manipulation things that are built for Python to use, you end up with this much more efficient way of getting data from the Python world into the Spark JVM, because you can just share the pointers to memory because of Arrow's universal format there.
The original configuration for this in Spark 2.3 was under Spark SQL Execution Arrow enabled, but in Spark 3 onwards, it's now under Spark SQL Execution Arrow PySpark enabled. This implementation was then later generalized for Pandas UDFs, Arrow optimized UDFs, Spark Connect, and eventually now the Arrow UDF that we natively have now in Spark 4.1. This then triggered a series of improvements across the board for UDFs in all of Spark, specifically including vectorized UDFs in Python, which was proposed initially by Reynolds Shin. Earlier work I just mentioned proved that Arrow could replace Pickle for data collection, and by Spark 2.3 it proved it could replace Pickle for UDF execution, one of the core performance bottlenecks of Spark. If we want to take a look at how this looks like after, with Pandas UDFs as an example for each batch of 10,000 rows, what changed was that the JVM would then convert the column to Arrow's record batch, and then write it to the socket. Afterwards, Python would read the record batch, convert the Arrow array to a Pandas series, and then call a function, convert the result to Arrow, and then write to the socket. The JVM would read the record batch afterwards and then convert it back to internal row. So for 10 million rows, we would have around 1,000 batch transfers instead of 10 million row transfers. The function itself operates on the Pandas series backed by NumPy. So if we take, for example, an arithmetic operation like price times 1.1, this then executes as a single vectorized C operation across the entire batch. Therefore, there would be no Python for loop and no per element overhead. Arrow in this case removes a lot of the serialization overhead that dominates simple operations. Complex operations, in contrast, benefit additionally from vectorized NumPy and Pandas execution versus the traditional per row Python execution. Each IPC message here is an encapsulated message. The stream begins with a schema message, including things like field names, data types, metadata, things like that, followed by one or more record messages. Each record batch would then contain flat buffers metadata, validity bitmaps, offset buffers, and data buffers. A record batch in memory looks a little bit different from maybe what we're used to. For instance, for a batch of 4 rows with given schema of name assigned to a string and an age which is perhaps type int 30 in this case, this is kind of what we expect to see. The H column here is a contiguous array of 4-byte integers. The name column uses an offsets array to index into a single contiguous UTF-8 buffer. No per value type tags, no escaping, and no framing overhead is needed. The batch size is then controlled by the configuration of Spark SQL.execution.arrow.max records per batch. This default is 10,000 rows. This determines how many rows are included in each Arrow record batch sent over the socket. The default is 10,000 because it's a balance between being too small, which results in excessive per batch overhead, or too large, which results in higher memory usage per batch, and poor pipeline parallelization. The sweet spot of 10,000 rows, which is around 100 kilobytes to 10 megabytes per batch, depending on the column types, tend to fit comfortably within the L2 and L3 cache. Now, let's move on to MapInArrow, which results in having direct arrow access for data frames. This is really the first direct arrow API introduced in Spark 3.3 in June 2022 by Hyukjin Kwon.
Talking about the MapInArrow itself, the motivation behind the MapInArrow was that, to be absolutely honest, it was to enable vectorized processing of nested data. Initially, I thought that the needs of dealing with this kind of nested data is not very large.
Essentially, before MapInArrow was introduced, every Python API that processed data in batches went through pandas. So even if you didn't need pandas, and in this case you wanted to use PyArrow's native compute functions, you had to accept the arrow to pandas to arrow conversion. MapInArrow was the first API that exposed raw PyArrow record batch objects directly. Why this mattered so much was because MapInArrow processes processed entire partitions as arrow record batches.
We added it, and then surprisingly, the community really liked it. It's actually being used a lot, like in the third-party integration.
Basically, from the JVM, you would have an arrow record batch, which would then move to the socket, and with Python receiving the entire record batch directly. So this way, you were able to call your function and then arrow record batch back to the socket and then back to the JVM. There was no pandas, no numpy, no conversion. The record batch your function received was the exact same binary. The binary data the JVM wrote to the socket. And so if PyArrow could wrap around the socket buffer directly, this ended up becoming a true zero copy on the receive side.
This is all built on the fact that the Spark can pass data from its JVM core into the Photon engine, back and forth across all these systems with a very low cost because of the usage of Arrow internally.
MapInArrow operates on whole partitions, like its MapInPandas equivalent. Later on in Spark 4, we would see that Arrow UDFs would be introduced that would then operate on individual columns. They complement each other extremely well because in this case, you can use MapInArrow for inputting entire record batches and then iterate on them while also outputting the same. The scope would be the full partition with every single column. However, with Arrow UDF, you could input an array directly for each column and then output the same as well. The scope of Arrow UDF is limited to a single column expression.
Pandas UDFs have allowed usage of Arrow for a long time. And Spark, even Spark 3, some of the later versions of Spark 3, took advantage of that and enabled that if you had it and there was a configuration value for it.
Spark 3.4 introduced the concept of zero effort migration, resulting in Arrow-optimized UDFs for Python. Arrow-optimized UDFs represent a different strategy than the traditional Pandas UDFs or MapInArrow. Instead of asking developers to rewrite their functions to accept Pandas series or PyArrow arrays, the feature instead replaced the serialization layer under the existing UDF functions while keeping the same per row function signature. The function would still receive one value at a time and return one value, but the data transported between the JVM and Python would now use Arrow instead of Pickle completely. The function is still call per row, however, the serialization is per batch. This eliminates the per row Pickle overhead while requiring zero changes.
One of the goal in the team is look into to improve the open source is to improve the debuggability because in the end we have a Python process running and then we that interacts with the JVM executor, right? And then we need a way to debug. If you want to debug, then there are multiple machines and then they're running around and then it's really hard to tell what's going on between the JVM machine and then the Python executor. But if we integrate everything into the Arrow, then you could have a very easy debug tools. You can just have a one way to see the what Arrow data inside and then you can unify the debugging tools.
Spark Connect was also introduced in the same distribution, 3.4, which used Arrow as its result streaming format. This is a different integration point than UDFs that we've been talking about because it's about how the query engine gets from a remote Spark server back to the thin client. For instance, in a Spark Connect client, you would have the Python application receive the Arrow stream and then reconstruct the data frame from the Connect server, which would then convert the results to Arrow record batches and then stream it over gRPC. In this scenario, the client sends unresolved logical plans serialized as protocol buffers to the server over gRPC. The server optimizes and executes the plan, and then it streams the results back as Arrow IPC record batches over the same gRPC channel. Before Spark Connect, PySpark ran Python and the JVM as two separate operating system level processes that communicated through Py4j, a socket-based bridge that lets Python call Java objects in a separately running JVM process. The results were then collected through Py4j's object-by-object bridge. However, with Connect, there's now no longer a need for JVM on the client itself. The PySpark Connect package ships only the Connect client libraries, Python plus protobuf and gRPC stubs, without any of the Java installation that would be required otherwise. The results will stream as Arrow, so the client will then receive Arrow record batches that can then be converted to Pandas data frames, PyArrow tables, or processed directly. This is pretty consistent with the same Arrow format used everywhere in the Spark Python ecosystem.
A lot of the Spark Connect libraries, even though they're using Arrow for the communication with the Spark system, they're still only exposing rows. And so my kind of ideal here is the Spark Connect libraries at the edges there should also expose expose Arrow output. It doesn't have to be the default, but it has to be an option.
Arrow persists as the common thread here. The same columnar format that moves data between JVM executors and Python workers can now also move data between remote Spark servers in a lightweight client process. Spark 4 started with a major investment within the Arrow ecosystem through one simple change, which is setting the configuration of Python UDF Arrow enable to default to true. This basically meant that every existing UDF in Spark code basically automatically benefits from Arrow serialization without any code changes on the user side. The upgrade was pretty transparent, but it showed the rising tide in strategy where even if code bases couldn't be rewritten, they could still get the performance boost just by upgrading Spark itself.
While Arrow is extremely efficient with the zero serializing, zero copy, and all that fun stuff, it is still expensive to go into and out of the Arrow format. So the longer you keep it in the Arrow format, the more efficient everything is, because it's still very efficient to operate in it.
Spark 4.0 also introduced the ApplyInArrow method, which is basically the Arrow native equivalent of apply in Pandas, where instead of receiving each group as a Pandas data frame, your function would now receive a PyArrow record batch. With apply in Pandas, the Arrow to Pandas conversions allocated memory and copied data for certain types, especially strings, timestamps, and nested types. For example, applying Pandas here follows the path of an Arrow record batch to a Pandas data frame, applying your function back to a data frame, and then back to Arrow record batch. This is considerable overhead. Applying Arrow eliminates this. It speeds up and scales with group size. For instance, if you had 100 rows, there would be an approximate speedup of about 1, which is relatively negligible compared to applying Pandas. But if we scale up to 1,000 rows, we see that there's a 1.5 times speedup, and at 10,000 rows, we would get up to 2 to 4 times speedup. In Spark 4.1, especially released this last December in 2025, we saw something completely different, which was a native Arrow UDF. Arrow UDFs are the newest and fastest Python UDF type. They are the culmination of a decade of Arrow integration work, the point where Arrow is no longer just a transport layer, but now an execution format for your UDF logic.
All of these things that enable Arrow interoperability just makes the ecosystem better because it gives you that modularity. You can put together a system that queries Spark and then takes the output and dumps it into a Polar's data frame that then dumps into DuckDB for post-processing, that then sends it to whatever you want. And the actual flow of the data isn't impeded by all of that format conversion. It gets to stay as Arrow as you flow from component to component, which just makes the entire system more efficient.
Previously, every single Python UDF type involved at least one conversion step. For instance, with Pickle, we had 4. JVM to Pickle to Python, and then back to Pickle, and then JVM. Arrow-optimized UDFs also had to convert from Arrow to Python, and the same with Pandas. The native Arrow UDF, however, has a total of 0 conversions because it just goes from JVM to Arrow and directly applies your function instead of converting it to Pandas series or a Python value. The Arrow UDF will receive your PyArrow array and then return your PyArrow array in this case. The data arrives from the JVM as Arrow, and your function processes it as Arrow, and the results go back to the JVM as Arrow. There's no format conversion at any point. This is actually an incredible performance boost because when you write something like a PyArrow compute function, in this case multiplying the price by 1.1, you're actually calling a C++ function inside of the Arrow library. This operates directly on Arrow's array memory buffer and is a contiguous array of 8-byte doubles. The C++ implementation can use SIMD functions, loop unrolling, and cache-aware iteration. Python is only involved in dispatching the call. The actual computation is native code. When we compare this to a Pickle UDF, for instance, where let's say the same function of price multiplied by 1.1 runs as a Python bytecode operation on a Python float object instead, resulting in all of the overhead that would be included with Python's object model, reference counting, and CPython's global interpreter lock. Okay, we've gone over a lot of different UDFs in this video. Let's try and review the different options that are currently available in Spark 4.1 and the performance hierarchy that we'll see there. The current most performant way to run functions in general are always going to be through built-in Spark functions, right? This is because they're Catalyst optimized and JVM code generated. And the second best option there is going to be your SQL UDFs, which are also highly performant. They're also Catalyst transparent and inline. So after that comes your Scala and Java UDFs, which are also JVM native and opaque to the catalyst itself. After that, we have Arrow UDFs, which I talked about in the Spark 4.1 distribution. This leverages zero-copy columnar transport in formats and C++ compute kernels directly. After that, we have Pandas UDFs, which are vectorized, but also contain Arrow to Pandas conversion. After that, we have our Arrow-optimized Python UDFs, which include Arrow transport, but still rely on per-row Python execution. And then in last place here, we have the Pickle Python UDFs, which are the oldest UDFs that we have in Spark, and are still row at a time and rely on Pickle serialization. As we can see, Arrow UDFs just sit below the JVM native UDFs, and they're the fastest option available to Python developers who need custom logic beyond what the built-in functions or SQL UDFs can express.
If there are few value in the very large data, like binary data, it's better to just don't use the Arrow itself. But the Arrow solved this problem by introducing the large binary type. So if a value is too large, then you can use the large binary type. Then the value of the data itself can grow over easily 2 GB. But it's problem of the Spark. The Spark is using the unsafe memory that's in JVM. So basically you're using the direct memory and stuff. And that has a limitation of the 2 GB. It cannot grow over the 2 GB. If you're, for instance, handling the very large, for instance, image or something, then the Spark might not work very well, from my experience, because those are the tickets that are addressed.
If you're coming into this with fresh eyes, however, you might actually want to think about how you want to build your UDF functions. If you can express and build it with built-in Spark functions, you should always prefer that because it's going to be the fastest. If you're also going to try and express it as pure SQL, it's also going to give you the best performance in this case. If you can express it with PyArrow's compute, then Arrow UDF's native functionality will help you much more as well. If you need Pandas, NumPy, or SciPy, then you should use Pandas UDF instead. For cases where you need traditional UDFs, but you want to leverage Arrow transport but still retain per-row Python, you should just use the use Arrow parameter instead.
The spirit of this project, I really liked it because it had the one unified format. It became from my perspective, it became the very standard the memory format that's been used. And it has been stabilized. I've been involved in the Arrow development in the last quarter. People are very conservative, and then they don't want to make a breaking change. So those kind of standard, and then those really great people who worked on the Arrow made this project very successful. And then this 10th anniversary, looking back, I see every project is using Arrow. Yeah, and the Spark is trying to use Arrow too. So congratulate. Yay.
Right now, as it stands, Arrow touches almost every single major Python to JVM integration point, from initially being used to replace Pickle for driver data collection, to its extensive use in the UDF system as a transport layer, to then also being the default result streaming format in Spark Connect, and then also a data source format in the data source API.
Till Spark 4, that we use the Arrow more IO level only. If you want to send the data between processes, then use the Arrow, right? Our team is now taking a look into the changing the core, switching the SQL data format itself to the Arrow, and then using that Arrow format in the a debugging tool, debugging data format and stuff. So yeah, so it'll be much easier to spot the Arrow integration in the upcoming Spark releases.
I hope you enjoyed this video. This was a really lengthy one to put together, and it goes very deep into the integration, maybe a little bit too deep, to be honest. But I was really excited to be able to share it with you. I hope you enjoyed this mix of history and open source and technology and the data engineering space, because open source projects actually have a ton of influence over each other, and depending on how the Arrow project evolves, Spark will also evolve too, and the both will actually be able to influence each other over time, depending on how new features develop and depending on who gets involved in the sort of open source work. I hope you enjoyed this content. Please comment below if you want to see more of this sort of stuff, or let us know what you want to see more of in general.